speaker is Joshua Warren from Yale School of Public Health, and Joshua is going to talk about a Bayesian framework for incorporating exposure uncertainty into health analysis with application to air pollution and stillbirth. Thank you.
Yeah, thank you, Monica, for the invitation and for organizing the session. It's an honor to speak here today, and thank you for everyone who's here listening. So, yeah, today I'm talking about some very recent work that I carried out with a student, Saskia Gomez at Stanford, and my collaborator, Howard Chang at Emory. I'll jump right in sake of time here. But in terms of exposure modeling, environmental health studies obviously require exposures to be linked to every observation in your health data set. So observations could be individuals, it could be time points if you're thinking of like a time series type analysis of health outcomes. However, because exposure data are typically not available at every location and time, predictions from a first stage statistical model are used to fill in the spatiotemporal gaps. So we would love to have people wearing monitors throughout their days, and so we can accurately quantify what they're exposed to, but this is often not feasible for large spatial domains, and so we rely on these, at this point, advanced statistical and even machine learning methods to combine observed monitoring data in the US from the EPA with auxiliary information like Monica was just talking about in terms of deterministic output in the form of CMAC, potentially, satellite data, lots of other things to statistically combine these things, usually via like downscaling to fill in these gaps. And many of these approaches are actually taking place within the Bayesian framework, which is important for what we're attempting to do in this work. So just as a kind of an example here in the work that I'll be talking about in a few slides, this is New York, New Jersey, and Philadelphia in Pennsylvania. And so the blue dots represent EPA monitors that were active at some point during our study period. The gray grid that you see in the background represents where we had daily measures of PM2.5 from the CMAC model, a deterministic chemistry model. And then we kind of combine these outputs via a statistical model to produce interpolated surfaces, not just focused on the predictions. However, there are distributions underlying every point that you see on the right here. So in this case, on this particular day in August, PM, for example, is highest near New York City and in Philadelphia. But the idea is that you take this raw data and you create some output via a statistical model. And so that was kind of the jumping off point for where we got started in this particular work. So then it's time, once your data are linked, to think about the health modeling. So the methods that we just talked about kind of vaguely provide samples from exposure posterior predictive distributions for each observation in your health outcome data set. So fully incorporating this information, not only like the center of that distribution, but also the uncertainty, the shape of the posterior predictive into the subsequent health analysis is really important for conducting accurate inference on the thing we actually care about, which is the association between health and exposure. Health observations that are linked with exposures with higher uncertainty should feasibly contribute less to the overall health effect estimate. However, previous studies often entirely ignore the uncertainty from these first stage models, use simple summaries of the posterior predictives instead, or implement some other ad hoc approaches to account for it. So for example, this again is in New Jersey where we were working. And on the left, these are predictions across 3 counties in New Jersey that we'll discuss in just a few minutes. The maximum PM2.5 level daily for this 5-year period. And what I've plotted are the means of the posterior predictive distributions on each day. However, it's important to know that for each point on this plot, there's actually underlying it a distribution of samples from this first stage statistical model. So while we present here the mean or the median of the distribution and plot it in a time series fashion, what to do about the fact that there's a lot of uncertainties for some days more than others, particularly, how do you incorporate the shape and the uncertainty into your health analysis as well, not just the raw point estimates? So the questions of interest that motivated this work are, given the PPD samples from the first stage model, what is the best way to incorporate all of its information into the second stage health outcome model? So it's important to note that we are focused on this very specific situation where the first stage model has occurred, possibly by a separate team, a separate group, and you are able to get access to these posterior predictive samples from all of your exposure data points. There are other methods that exist, for example, the parametric bootstrap, but it requires you to refit the first stage exposure model time and time again to account for the uncertainty. So we're focused on situations where the posterior predictive samples are available and how to use those in our health model. What are the implications of using existing approaches or entirely ignoring this uncertainty? Hopefully it's not bad, because a lot of my work before this has done just that, ignore that uncertainty to a large extent. And generally, can we develop a computationally tractable and somewhat general solution for different health outcomes? So health outcomes come in very different forms. You can have a continuous, like birth weight. I deal a lot with pregnancy outcomes, so I'm dealing with binary, low birth weight or not. Preterm pregnancy, you can have counts of diseases across space and time. So we want a solution that's somewhat generalizable so that we can use it for lots of different outcomes. So the contributions of this work that we're about to discuss are, we propose use of Gaussian kernel density estimation to define the exposure prior distributions for the health outcome analysis. And we show that this framework allows for improved characterization of the shape and uncertainty of these exposure posterior predictives, while really importantly, maintaining computational benefits similar to previous approaches. So it's easy to model something flexibly, but you often pay the price computationally. And so we were able to show that we can do both in this case. And so we were able to develop an R package that hopefully will be useful moving forward for people in a similar situation. So we developed a simulation study and showed that KDE leads to improved estimation of the health effect of interest compared to some existing approaches. And finally, we apply some of these approaches, including the new one, to understand the relationship between population level PM2.5 exposure and stillbirth risk in New Jersey. So just a little notation to get everyone on the same board. So this is the output from the stage one model. So Z star is a matrix, an N by M matrix, where N is the number of health data points you have. So it could be the number of pregnant women in your study or the number of time points you're interested in. And M is the number of posterior predictive samples you have. So every row represents the full collection of posterior predictive samples for observation one, for example. And then columns represent a MCMC posterior predictive sample collected for iteration J, and then all the way to M. So these are what we're using as input to the health exposure model. The health outcome model, I mentioned we really wanted it to be general, so we're not focused on linear regression or logistic regression or Poisson or negative binomial. We're keeping it very general at this point, very vague. But so we're assuming some exponential family, some link function, where we have potentially an offset variable. We have our typical vector of covariates confounders having nothing to do with the exposure of interest. And then this red Z, I'm going to denote it as red moving forward to let you know that this is the true but unobserved exposure for person or time point I. So we would love to know Z. We don't know Z, but we do have information about Z through the posterior predictive samples. So through row I of Z star, for example. So what we really care about in the health model is this theta parameter. We want to know is the exposure associated with the outcome in some way. So the question that motivated most of this work is how to connect that stage one Z star matrix of posterior predictive samples with the stage two health outcome analysis. So we'll talk a few minutes about some current approaches. The simplest and the thing that's been used most often is this plug-in exposure approach, a really conceptually and computationally simple approach. In the health model, you replace the red ZI with some function of the Z star matrix. So you can think of taking the mean or the median of the different rows of Z star and just using that as a predictor, an estimate of the exposure for person I, for example. Another approach that's been used quite often is multiple imputation. And instead of summarizing the Z star matrix in that way, you actually run the analysis M times, one for each column of Z star. So you're plugging in a new set of exposures for ZI for the Z matrix in this case, the red Z vector in this case. You run the analysis on every single posterior predictive sample that you collected. And in the end, you're doing this in a Bayesian fashion, at least in my mind. You pool all of those posterior samples together and make inference on theta. However, MI is known to produce biased effect estimates because it doesn't condition on the health outcome data when selecting, and I put selecting in quotes here, columns of exposure. So you essentially equally weight all of those columns as if they're all valid columns of exposure. But what happens is you end up diluting the true signal with a lot of noise if some of those columns are far away from the true exposure. So there's an approximate version of multiple imputation because that can obviously take a long time. If your MCMC model takes a few hours to fit for one data set, you can imagine having to do that 10,000 times. So the multiple imputation approximation serves as an approximation to that, where essentially in one sweep of your MCMC algorithm for the health model, you're randomly selecting with replacement from one of the columns of Z star. So you still get that variability across the posterior predictive samples, but you do it within one model fit. So this requires only a single model fit, and we show, at least in the simulation study, that you get very similar results as to the full MI process. So Chang, Howard and Roger Pang developed, I think in 2012, the idea for this discrete uniform prior distribution. So essentially, it's the first, at least of the methods we're discussing, that put up an actual prior distribution on the vector Z, the red vector Z. And it says that Z can only take one of those M vectors from Z star. So you essentially are making this really tough assumption that one of the vectors of your Z star matrix are the true vector of exposures. And by putting a prior that's discrete in this way with equally weighting all vectors, you're asking which one is it. You're trying to learn from the data, from the health data, which one most aligns with the true vector of exposures. Similarly to DU, the multivariate normal prior distribution also puts a prior on the red Z, the true vector of exposures. And it does so in a different way, however. It doesn't restrict it to the columns of Z star, so you're no longer restricted, but it summarizes those columns in those rows, actually. So it centers it at the means of the posterior predictive distributions and the variance covariance matrix of that full matrix Z star. So in this way, it accounts for the correlation and kind of the centers of the distribution. So I think it's important to talk about what it actually looks like to work with these two prior distributions, in particular DU and multivariate normal, and what it looks like to compute these things. So in your MCMC algorithm, you have a full conditional distribution update for the true vector of Z for each of these prior models that you've specified. So for DU, what this actually looks like is each time in each iteration of your algorithm, you're proposing a new column of Z star, a new vector of exposures, and you're asking, is this one more probable than the one I'm currently at? If so, you make that move in that direction. If not, you stay where you are. So for DU, you're kind of homing in on the most probable set of exposures, for example. And so the one issue is that, as I mentioned earlier, you're limited to the collected PPD samples you have. So hopefully the true vector of exposures or something similar to that is in that matrix. If not, you're somewhat out of luck. On the other hand, multivariate normal, you end up drawing a brand new vector of Z from some multivariate Gaussian distribution that's blending the health data with those summaries of the PPD samples from Z star. So we like both of these intuitively. We like that DU is distinctly using those Z star matrices. It's actually using the samples that you've collected. Multivariate normal, we like that you're not restricted to only using those samples. So if we could somehow combine both of these ideas, we think it would be potentially a more powerful approach. And so this is where we thought about something slightly more flexible than both of those, we think, kernel density estimation prior distributions. So we use this form of a Gaussian kernel density estimator, and it centers, so it's a mixture of equally weighted normal distributions, M being the number of posterior predictive samples you collected, and each one is centered at one of the entries of the Z star matrix. So this H is your typical bandwidth parameter that you estimate out of sample here to get the shape of that posterior predictive right. So In this case, in the univariate version, these priors are calculated independently for all zi, I equals 1 to n. We did in the manuscript try a multivariate version of KDE, which conceptually made even more sense. Unfortunately, it was very difficult to do this multivariate extension because of the high dimensionality of most of our exposure data sets and our health outcomes. We're dealing with much bigger sample sizes than some of these multivariate KDE approaches were designed for. To give you a sense of what this looks like for one of our New Jersey maximum PM 2.5 posterior predictive distributions, the red line here represents the plug-in approach, where we've just taken the median of this distribution, and we would use that as Z in the health outcome model. The blue represents the multivariate normal prior distribution based on the center of that distribution and the variance covariance of the full vector of Z star. You can see that it kind of misses part of the heavier tail, and it gives too much weight here because of the symmetry required of the multivariate normal. However, our KDE approach, as we know, KDE is going to do a nice job of replicating the shape, potentially overfitting in the tails, but none of this matters. So like, we're happy that we can match the shape better, but none of this matters if computationally you can't work with this form. So what we showed is that computing KDE actually is very intuitive for several different outcome types. And so you can actually write down full conditional distributions that have closed forms, very useful for MCMC sampling. And so I'm not going to show you all the details here. I'll reference the paper later, but it breaks down to 2 steps. Because it's a mixture of univariate Gaussians, the first step is highly similar to discrete uniform. You look at all of your columns, you calculate basically the probability for each column, and then you randomly sample from those probabilities and select a column of exposures that most closely align with the health data and the exposure model. So in the DU world, you're stuck there. You use those exposures and move forward in your regression for the health outcome. However, in the second step, because it's a mixture of multivariate or mixture of normals, then you're actually drawing a new vector of exposures where it's centered at the health data and this recent vector of posterior predictive samples you've drawn. So in this way, it blends both discrete uniform and multivariate normal together. And so we really like the intuition here. So we designed a simulation study where we looked at lots of different ways of characterizing the Z star matrix, where it was skewed, it was correlated, it had larger variance, smaller variance. Important to note that the true exposure was simulated from the same models that simulated samples from the posterior predictive distribution, but it was not included in Z star. So we did not assume that the true vector of exposures, that we were fortunate enough to have it show up in the Z star matrix. And so all of our testing is basically how well can we estimate theta using these different approaches. And so just to give you a sense of what some of these simulated data sets look like, you have some skewed with uncorrelated, you have skewed with correlation. So we ran the gamut here on a lot of different outcomes. And I'm going to show you a big table of results. The thing to take away from it first is that the blue values suggest optimal performance in terms of estimating theta and bias, mean squared error, empirical coverage, power, etc. And you can notice first off that UKDE does a really nice job across a number of different correlation and skewness settings. Luckily, plug-in approach actually does pretty well overall, unless you have skewness. If you have skewness in the PPDs, those plug-in estimates get pulled to the tails and you're possibly mischaracterizing exposure. Surprisingly, to us at least, these 3 approaches in the middle, the multiple imputation and DU, tend to pull things towards the null. And looking back, it was intuitive, but at the time it was surprising. And we'll show a little bit about that in that actual case study as well. Another way to view these results is these are box plots of the posterior mean estimates of theta from the health analysis. And you can see that the UKDE results are generally around the truth, which was in this case 1 for lots of different settings, where other methods tended to pull towards the null, for example. So on to the Stillbirth, New Jersey data application. We focused on 3 counties in the New York, New Jersey metropolitan division. Fetal death is a death 20 weeks or after or a stillbirth. And we focused on a time series analysis where we were modeling maximum at different lags PM 2.5 concentrations with daily stillbirth counts. Here's the study area. Here's stillbirth proportions over time, where 71% of days we had no stillbirth in these 3 counties. Not going to go into much detail here, but just know that we carried out our own stage 1 exposure modeling. So we had full control over the PPDs that came out in terms of the Z-star matrix. We basically modeled the observed pollution as a function of CMAQ data, where we had spatially and temporally varying regression parameters to allow for extreme flexibility across space and time. And again, this left us with, on every day of our study, we had a little posterior predictive distribution to work from, where we could define these different approaches. Our health outcome model, because we were working with counts of stillbirth across days, we modeled it using negative binomial regression as a function of day of week, calendar time, min and maximum temperature, model with splines. And then finally, what we actually cared about, PM2.5 exposure at different lag Ls. And so we fit multiple lags at separately in these models. So we're really interested in what's the association between stillbirth and maximum PM2.5 across these counties. Jumping to the results here. So on the x-axis, we have different lags that we considered based on kind of biological mechanism for stillbirth and previous literature. And we see that on 3 days prior to delivery, it looks like increased PM2.5 exposure leads to increased risk of stillbirth counts in the population as a whole. What we see here resembles very closely what we saw in the simulation study, which gives us some confidence that how we simulated the data made sense. So the multiple imputation approximation approach, as we saw in the sim study, tended to pull things towards the null, as did discrete uniform. The other approaches in this case were fairly similar. We saw more variability for plug-in, just as we saw in the simulation study. We also carried out a fully joint analysis, which in some ways is the gold standard, but often computationally really difficult if you have lots of exposure data and lots of health outcome data, because you're constantly feeding back and forth between the two within a single framework. So yeah, it looks like, what we learned in the simulation study may hold, at least for this particular application. In conclusion, it looks like KDE may be a flexible and promising approach for characterizing the uncertainty and the shape using posterior predictive samples. Simulation study results suggest that it led to some improvements regardless of the true nature of the PPDs. And we saw some signal at 3 days prior to delivery in New Jersey. And we're currently working on extending some of these ideas to critical window estimation, where you have within a single observation, time varying exposure in a model. And here are some acknowledgements, funding, and Saskia, a PhD student, and Howard, my close collaborator for a few years now. So thanks for your attention.
Thank you so much, Jasper. So we have a question in the chat.
Okay.
And I'm going to read it. So, great work. You said that the normal approximation for Z was insufficient because the lower tail was too heavy and the upper tail was too light. So it sounds like something a transformation could handle. Have you considered something like a log normal for Z, or using an exponential or box-Coq?
That's a really great question. And in past work, when we've used this multivariate normal idea, we've done just that. We've transformed to achieve as much normality as possible. So yeah, that can often do the trick in terms of getting something more approximately normal, but we still think there will be cases of heavy tails, especially if you're focusing on extremes, for example. We know there will be some lingering tails. We also aren't always sure in the health outcome model, the correct transformation with respect to the pollution. So should it be on the original scale, or should it be log scaled or square root transformed? That can sometimes alter the associations that you're actually estimating with theta. So there could be reasons you wouldn't want to transform, I guess, in practically speaking, but from a statistical perspective, yes, trying to achieve normality is always a good idea, I think.
I think we have another question.
Yeah, so we focused on, it turns out if you have enough posterior predictive samples and you're focusing kind of one observation at a time, as we did here, you can generally estimate the shape pretty well. Now, we didn't try these crazy examples where you had multiple modes, because we haven't actually encountered posterior predictive distributions for exposure that look like that. So we were trying to make things realistic as possible. But you're right, especially in the multivariate version of KDE, we could not get something, everything was too sensitive. So whatever choice we chose for the bandwidth, in that case, covariance matrix, it led to very different results. So in the paper, we go through this multivariate version, but we found the univariate version be very stable, especially for the types of exposure kind of distributions we're dealing with in general. And I guess I'm thinking of air pollution. So there may be other reasons why you need to be more thoughtful about the bandwidth parameter, but we were using the a version where you were actually fitting and estimating that bandwidth parameter outside of the modeling itself.
Okay, so thank you so much, and thank you to all our speakers, Ben, Eliane, and Joshua. And